If your boss demands loyalty, give him integrity. But if he demands integrity, then give him loyalty. Colonel John Boyd. Today we're going to cover airplane instruments and engine systems. We'll start with a short scenario. I'm going to give you a chance to talk about your most recent flight. We'll get into airplane instruments and engine systems, and then we'll do a quiz and assign some homework. Let's take some time now to practice interpreting our instruments. Looks like we're in a nose high attitude. There's a stall. Nose low attitude. Airspeed's increasing. Our vertical speed is going up. Looks like we're in a left turn, uncoordinated. The wings level, now we're descending, slowly becoming coordinated. Airspeed's increasing. Power just went down. Power's up. Vertical speed decreasing. We're in a descent, very steep descent. Nose low. Uncoordinated. Wings level. Nose high. All right, now take a moment to debrief your most recent flight. What was the objective of your flight? What went well and what could have gone better? And what was your favorite part of the flight? Let's talk about the compass. The compass is one of the oldest and simplest instruments for indicating direction. It's a little piece of metal that attracts and holds lines of magnetic flux, and there are two poles, the North and the South Pole. The compass consists of two small magnets attached to a metal float sealed inside a bowl of clear compass fluid similar to kerosene. There is a graduated scale compass card wrapped around the float. Remember that the compass is only accurate in straight and level flight, and deviation is error caused by the metal inside the aircraft. What are the two poles of a compass? North and south. When is the compass accurate? Only during straight and level, unaccelerated flight. There are some errors associated with the compass. We use the acronyms ANDS and UNOS to remember them. ANDS stands for accelerate north, decelerate south. If your aircraft is on an east or westerly heading and we accelerate, it's going to indicate, the compass will indicate a turn to the north. If we decelerate while on an east or westerly heading, the compass will indicate a turn to the south. UNOS stands for undershoot north and overshoot south. If we are flying a northerly heading and we make a turn, the compass will undershoot that turn. It might even indicate a turn in the opposite direction and will eventually catch up to your turn. While if we are on a southerly heading and we make a turn, the compass will overshoot the turn and indicate that we are turning faster than we actually are. What are the two acronyms we use to remember the compass errors? UNOS and ANDS. Let's move on to the pitot-static system. The pitot-static system consists of three instruments: the altimeter, the airspeed indicator, and the vertical speed indicator. What three instruments are part of the pitot-static system? The altimeter, airspeed, and vertical speed indicators. What are the two acronyms we use to remember the compass errors? UNOS and ANDS. Let's talk about the airspeed indicator. The airspeed indicator takes ram air from the pitot tube and compares it to static air. The ram air pushes against this diaphragm, which gives us an indication of our airspeed. The airspeed indicator is color-coded to make it easy to read while in flight. The white arc on the airspeed indicator indicates the flap's operating range. The bottom of the white arc is our stall speed. The green arc is the normal operating range. The bottom of the green arc is our stall speed in a clean configuration. The top is the max structural cruising speed. The yellow arc is the structural warning area. It's a caution area. And the red radial line is the never exceed speed. VA, our maneuver speed, is not shown on the airspeed indicator, so you should consult your POH. Let's talk about the altimeter. We first set our altimeter setting from our ATIS or weather information here, and that sets the aneroid wafers in a certain position. Then the altimeter takes static air from the static port and puts it into this chamber here. And the change in pressure will expand or contract these aneroid wafers. And as they expand or contract, they will give us an indication of our altitude. It's read like a clock. The short needle indicates 10,000 feet, the medium needle indicates 1,000 feet, and the long needle indicates 100 feet. And it's numbered from 1 to 9, or I guess 0 to 9. All right, quick, explain the compass errors. We use ands and unos. Accelerate north, decelerate south, and unos, undershoot north and overshoot south. What 3 instruments are part of the pitot-static system? The altimeter, airspeed indicator, and vertical speed indicator. Let's talk about the vertical speed indicator now. Similar to the altimeter, the vertical speed indicator takes static pressure and puts it into this diaphragm here. There is a calibrated leak that allows air to come in and leave the chamber here. As long as the air pressure inside the chamber and inside the diaphragm are the same, the vertical speed indicator will indicate 0, or a 0 foot per minute rate of climb. If there's a change in pressure in our static air, it will either expand or contract the diaphragm until the pressure equalizes inside this chamber. And while there's a pressure differential, this vertical speed indicator will indicate a climb or a descent. So to recap, the VSI gives us a rate of climb or descent in hundreds of feet per minute. It tends to lag, but it is an excellent tool for stable landings. Let's review the compass. What is deviation? Deviation is error caused by metal inside the aircraft. What are the 2 poles of a compass? North and south. When is the compass accurate? Only during straight and level, unaccelerated flight. Let's talk about different types of altitude. Absolute altitude is the altitude above the surface, and it's given in AGL, or above ground level. True altitude is the distance above sea level and is in MSL, or mean sea level. Pressure altitude is the altitude we get when we set our altimeter to 29.92 inches of mercury. Density altitude is the pressure altitude corrected for non-standard temperature, and this is what the airplane feels like it is flying at. Indicated altitude is the same as true altitude when standard conditions exist, and the altimeter is calibrated correctly. Remember that standard conditions are 29.92 inches of mercury and 15 degrees Celsius. Pressure altitude and true altitude are the same when standard conditions exist. Setting the altimeter. The indicated altitude increases when you change the altimeter setting to a higher pressure and decreases when you change the setting to a lower pressure. There is an opposite reaction due to changes in air pressure. The indicated altitude will change 1,000 feet for every 1 inch of pressure change. For example, if we change our altimeter setting from 29.15 to 29.85, we subtract 29.15 from 29.85, multiply it by 1,000, and we get an altitude change of 700 feet. Let's talk about some altimeter errors. Altimeter readings are adjusted for changes in barometric pressure, but not for temperature changes. An airplane will be at a lower than indicated altitude when flying in colder than standard temperature when maintaining a constant indicated altitude. When pressure lowers en route at constant indicated altitude, your altimeter will indicate higher than actual altitude until you adjust it. Remember, from high to low, look out below. Let's see what it looks like visually. If you are flying in standard temperature air and you move into colder air without changing the altimeter, remember, from high to low, look out below. Your altimeter will indicate that you are at the same altitude, but you will actually be at a lower altitude. Alternately, if you're going from standard to warmer air without changing your altimeter, you will be at a higher actual altitude than what your indicated altitude is telling you. So from low to high, clear the sky. Now let's talk about pressure. The same rule applies. From high to low, look out below. If you are moving from standard pressure air to low pressure air, from high to low, we will be at a lower actual altitude than our indicated altitude suggests. And from low to high, clear the sky. From low pressure or standard pressure to higher pressure, we will be at a higher actual altitude than our indicated altitude. Let's recap. What is absolute altitude? That is altitude above the surface. What is the distance above sea level called? That's true altitude. What is pressure altitude? That's the height above the standard datum plane of 29.92 inches of mercury. And density altitude? That's pressure altitude corrected for non-standard temperature. Let's review altimeter errors. We're flying in standard temperature air, and we fly into cold air. Where will our aircraft be if we don't adjust our altimeter? We will be lower than our indicated altitude. Remember, from high to low, look out below. Let's move on to gyroscopic instruments. The three gyroscopic instruments are the attitude indicator, the turn coordinator, and the heading indicator. The attitude indicator is like a little simulated airplane here. The orange wings and the dot here represent our aircraft. Above the horizon is blue, so that's the sky. Below the horizon is brown, that's the ground. The attitude indicator also gives us angles of bank and angles of pitch. So if we have the orange nose above the horizon, we are in a climb or a nose high attitude. If it's below the horizon, we are in a nose low attitude. If we have wings turned to the right, we are in a level right bank, and wings to the left, level left bank. The turn coordinator is an electrically driven gyroscopic instrument. This tells us information about the quality of our turn. If we see the wings pointing to this little line here, or this one over here, we are in a standard rate turn, and we will make a 360-degree turn in 2 minutes. We want to see the ball centered here. That tells us that we are in a coordinated turn. If the ball is off to the right or to the left, we want to step on the ball and go to this, a coordinated turn. The heading indicator is our third gyroscopic instrument. The heading indicator displays headings based on a 360-degree azimuth with the final zero omitted. Due to precession, we must periodically realign the heading indicator with our compass to make sure that it is accurate. If we exceed certain bank angles, the heading indicator may spill or tumble, and so we might need to recover using the caging knob. What are the three gyroscopic instruments? The attitude indicator, the turn coordinator, and the heading indicator. Let's move on to the glass cockpit. In the G1000, we have two screens. There's the PFD, the primary flight display, and the MFD, the multifunction display. The primary flight display basically gives us our six-pack, and the MFD can give us everything from primary instruments, moving map, onboard weather, checklist, and fuel management systems. This is what the PFD looks like. So just like before in the analog gauges, we have the airspeed indicator, the giant attitude indicator, the slip skid indicator, the altimeter, vertical speed indicator, and our horizontal situation indicator. Now this guy is really cool because it combines several different instruments into one. At the top of the HSI is our turn indicator and will tell us if we are in a half rate or a standard rate turn. We have our heading bug. We can include our VOR or GPS navigation. Here's our altimeter setting. Attitude indicator has, the little airplane that we fly with the wings here, and angles of pitch and angles of bank. Moving on to engine temperature. Excessively high engine temperature will cause loss of power, excessive oil consumption, and excessive wear. Remember that the engine is cooled by circulating oil that is used to reduce friction and absorb heat from internal engine parts. This is how to exceed normal operating temperature. Operating with too much power, climbing too steeply in hot weather, using fuel that has a lower than specified octane rating, operating with too lean a mixture, or the oil level being too low. Basically, all these are things that you don't want to do. Let's talk about the constant speed propeller now. The advantages of a constant speed propeller are that it allows you to select the optimal blade angle for most efficient performance. In a constant speed propeller, the throttle controls power output, as read on the manifold pressure gauge. The propeller lever controls engine revolution, or RPMs, on the tachometer. Remember, don't overstress. Avoid high manifold pressure with low RPM. For takeoff, we want to have the prop control forward and the throttle control forward. There's another video I made regarding constant speed propellers, and I'll link it down in the description. So on a constant speed propeller, the throttle controls power output. This is read from the manifold pressure gauge. The propeller lever controls engine revolution, and the instrument we use to monitor this is the tachometer. The engine ignition system is a dual ignition system. It has two magnetos. This improves the engine performance and increases safety. Remember, loose and broken wires can cause problems. If the ignition is off, the magnetos may continue to fire if the ground wire is disconnected. If this happens, move the mix to idle and then get a mechanic. Excessively high engine temperature will cause loss of power, excessive oil consumption, and excessive wear. The engine is cooled by circulating oil. And what does the oil do? It reduces friction and absorbs heat from internal engine parts. All right, pause the video now. Take 5 minutes to jot down everything you can remember from memory, and then we'll get into the quiz. Ready? Pause. All right, let's hit it. When does P factor cause the airplane to yaw to the left? At high angles of attack. An airplane said to be inherently stable will require less effort to control. During a spin to the left, which is or are stalled? Both wings are stalled. In the northern hemisphere, a magnetic compass will normally indicate a turn to the north if an aircraft is accelerated while on an east or west heading. The pitot system provides impact pressure for which instrument? The airspeed indicator. Which marking identifies the never exceed speed? The red radial line. What is absolute altitude? The vertical distance of the aircraft above the surface. To receive accurate indications during flight from a heading indicator, the instrument must be periodically realigned with the magnetic compass as the gyro precesses. What is a benefit of flying with a glass cockpit? Situational awareness is increased. An abnormally high engine temperature indication may be caused by the oil level being too low. How is engine operation controlled on an engine equipped with a constant speed propeller? The throttle controls power output as registered on the manifold pressure gauge, and the propeller control regulates engine RPM. All right, we made it. Your homework is to go review the G1000, read the Airplane Flying Handbook, chapters 4 through 6, and the Pilot's Handbook of Aeronautical Knowledge, chapters 4 through 6, and test yourself. Do 10 questions per day. I would love to hear your feedback. If you want to send me a message or reply to this video, love to hear what you have to say. And here are my references. Thanks for watching. See ya.